Let's keep going with our analysis of multivariate functions. Suppose we have a Cobb-Douglas function, much like the one we saw in the previous slide, and we want to know how y will change if hours worked changes just a little. Well, we can do that by computing the rate of change with respect to WRT, labor, holding A and K constant. Now, usually A is a constant, so it's never allowed to change. But here we're going to hold K constant, even though it's a variable and by definition it's allowed to change. But we're going to hold K constant here. When we find the derivative, y with respect to L, and we hold K constant, this is called the partial derivative. You can think of it like your introductory microeconomics class. You had an instructor that told you that we're going to hold all else the same. And that's exactly what we're going to do here. We're going to allow L to change, but we're going to construct the derivative such that the other variables are being held constant. Now we have an example to work on. Compute all the partial derivatives and interpret the rate of change. We've been given an example to work on. It says compute all partial derivatives and interpret the rate of change. I'm just going to focus on partial derivative with respect to capital, and I'll leave labor for you as an exercise. So to get started, I'm going to use my notation for a partial derivative. It's this kind of curly d, and I'm going to take the derivative of the function, or the derivative of y, with respect to k. And we've got a constant a, and we're going to keep labor fixed. So labor is going to be a constant here. It's not going to change when k is changing by construction. So I've got a. I could just write my constant out. It's not going to be allowed to change. And then the power rule, we're going to apply the power rule to k to the power of 1/3. So the exponent comes down, and we have k multiplied by k to the power of 1/3 minus 1. And we can do some simplifying here to better interpret the result. 1/3 minus 1, that's like k to the negative 2/3. And I could also write this as a, well, maybe I'll put the 1/3 at the front. We've got an a, we've got our L, 2/3, and I can put the k into the denominator, because the negative, it's like if I put it in the denominator, I can write it as a positive. And I can even simplify this further. I've got 1/3 times a L over k to the power of 2/3. Right, written very succinctly. Now, what have we computed here? Well, this is the marginal product of capital. So if we were to increase capital by a little bit, this is how much y will go up, y being output or real GDP. Marginal product of capital, we can say that the marginal product of capital is greater than 0, and that's because each of these multiplicative factors are positive. 1/3 a, L, and k, and a, L, and k are positive sort of by construction. We can't allow them to be negative. There's no such thing as negative hours worked. One last thing that's kind of interesting here is notice that if we increase labor, then the marginal product of capital will also increase. And so labor and capital here have a complementary property. Right? If we increase labor, that labor is going to be more productive if it has more capital equipment to work with. As an exercise for yourself, I encourage you to derive the marginal product of labor, and you'll get a similar result.